We're on page 2 of our guide, just to get us oriented. And tomorrow you're going to go with Dr. Fiddler and explore this little southwestern corner of the Whiteside Pluton down here. We're on the northern end, and that little red oval is where we're going, kind of where the hike is. We're just over here on the edge of the Toxaway Gneiss. And so it has a number there. And that number, what does that number mean? Yeah, but what is that? If you're going to tell someone quickly, what is that number? It's 1 billion years old. So we are standing, these rocks behind us are 1 billion years old. So rocks that are 1 billion years old were formed before Pangea. They are from the supercontinent Rodinia, just by virtue of their age. How do they know there was a supercontinent Rodinia? That's a very complicated explanation, but it is based on that. You go around the world, you find a series of rocks that are 1 billion years old, and you can say, okay, these must have been formed during another supercontinent like Pangea. So the Pangean rocks are more on the order of more like 3 to 500 million years old. So this is twice as old. So Rodinia broke up, much like Pangea is broken up. 250 million years ago, we stopped, Pangea stopped being assembled, and the proto-North America called Laurentia and Gondwanaland, actually, those are what broke up after Rodinia. Now we can say they're North America. They broke up into North America and Africa. But originally, when Rodinia broke up, you had Laurentia, which was proto-North America, and then you had Gondwanaland, which was proto-Africa, and the ocean that formed between them was called the Iapetus Ocean. And you'll notice if you go to go to the rock units on page 10, right here, it says the range is a continuum of lithologies and indicates sedimentary origin, the Tallulah Falls. So that's an example of where you need to fill data in. And down here at the bottom of page 10, where it says and so they also have a term, that they associate, and they call these rocks, the age was the Grenville age. So they call them Grenvillian rocks. But Rodinian was assembled during Grenville time. And so they, talked about, and when Rodinia broke up, there weren't just, Laurentia and Gondwanaland, there were a bunch of other stuff in between, and things developed during that formation of the Iapetus Ocean, which is what I'm putting right here. So that's Iapetus. And the Toxaway Dome, which we go back to page 2. It's also named the Toxaway Gneiss, but the feature is referred to as the Toxaway Dome. And I have a visualization on page 4, which shows what was going on in the ocean at that time between Laurentia and Gondwanaland in the Iapetus Ocean. And this is showing you that you've got what you'd expect, oceanic crust, but in the middle of it, you had this rifted continental basement. That means that when Rodinia broke apart, there were other chunks and pieces that, were it wasn't there was just all Laurentia and Gondwana land, you know, because we have this anomalous chunk of toxaway gneiss here, which is much older than everything else around it. So, you know, these visualizations are people's attempt to make sense and try to, like, you know, roll back geologic time and say, okay, how would this get here and where did it show up? And the reason that they show it with Tallulah Falls being deposited over it, because we drove past a place and we could spend all day just getting to here, assembling the geology between, you know, where we came from down in the inner Piedmont. Clemson's down in here somewhere. And we drove through, crossed this major fault zone called the Brevard Fault Zone, and then entered this blue stuff. And this blue stuff, it's called the Ash Metamorphic Suite, but it's also called the Tallulah Falls Formation. And the Tallulah Falls is what I call it on that side of the eastern side of the Brevard Fault Zone. But those are the rocks that we have in Clemson. But between Clemson, which is down here, and the Brevard Fault Zone, we cross a major thrust fault called the Seneca Fault, which we go into something called the Walhalla thrust sheet. You don't have to remember all this. But then we crossed another. This is what we did today. We crossed another fault called the Jocassee Fault, or the Eastatoy Fault, went into the Jocassee thrust sheet, and then finally went through the Brevard Fault Zone as we were coming up the mountain. But there's a lot of heavy trucks coming from the quarry, because they're just built like crazy out here. Anyway, we skipped all that inner Piedmont geology and jumped. So when you go, the Brevard Fault Zone marks the transition from the inner Piedmont to the Blue Ridge. So once we kind of climbed on up, hit the top, we were on the Blue Ridge, which we're now. So let's go back and look at this for a minute. Figure 2. So this is our setting. This is our Iapetus Ocean. You know, you have, you know, oceanic crust underneath there somewhere. And then looking at the stratigraphy in the inner Piedmont, these are all the sediments that accumulated, that were, you know, formed the inner Piedmont rocks. The only rock type that made it over the Brevard Fault Zone that was formed in the Iapetus Ocean is this lower one, the Tallulah Falls. And so I'm assuming you're familiar with this type of phenomenon. I showed it just in case. You're not accustomed to looking at thrust faults, but what we basically did was went through 2 major thrust faults on the way here, and then this major physiographic province fault, this complicated thing called the Brevard Fault Zone, and we could spend several hours just going through the Brevard Fault Zone, looking at all the curious rocks that occur in there. It's a fascinating section, because in there you can actually find marble, graphite. It's crazy. All this has gotten, you know, so as these thrust sheets were coming, or these packages of rock were getting thrust up and over, they were dragging stuff at the bottom, and they think that if we drilled down far enough at Clemson, we would hit limestone down there somewhere. That was part of Laurentia before all this other stuff was pushed on it, because the rocks that we see that formed in this ocean, when the Pangea started to get assembled, and there were 3 distinct orogenies they've identified, and they've identified all these orogenies based mainly on folding, and now we have lots of age dating, and we can say, okay, this was, you know, but those orogenies are all just, you know, they're dreamed up. They're educated guesses about looking at the rocks here. But all this stuff in that ocean, when everything started to get crunched together, you know, and first you had to get rid of the ocean, which meant that you had to have subduction. So during subduction, what happened to the oceanic crust? It went down. What about everything else? It went up. So that's what happens during subduction when you have all this, you know, lighter continental sediment sitting on top of oceanic, is there's a split. And if you go to the West Coast, Oregon is a great place, you'll see this happening. And like it's happening right in front of you. Of course, you know, have to use your geologic imagination, but there are entire ranges in southwestern Oregon that are made entirely of what's called ultramafic rock. Entire coastal ranges. And that's the stuff that's way down here deep in that oceanic crust. So they get split. So the toxaway got carried along. So as these sediments were getting pushed and metamorphosed and getting thrust over, they were also moving hundreds of miles in this direction. So everything we see here came from really far away. It did not, none of the rocks we see here formed here. They were subducted. I mean, whether the whiteside gneiss, which we're going to go take a close look at, you know, if we go back here, this yellow pluton, the whiteside, we're going to look at that interaction between the whiteside pluton and the blue, which is we'll just call it the ash metamorphic suite, because that's the accepted and this extends up into North Carolina. We're in North Carolina, but all the way up into here and into South Carolina, into Georgia as well. You know, and what I was saying, if somebody had drilled at Clemson and eventually you should hit what they call the decollement, and I'm not going to hold you to that, but it's DECOLLMENT, the decollement, that's the base of all these these packages of rock are sliding on as they get shoved this direction. So parts of the decollement are found in that, you know, Brevard fault zone. So we're only going to see the Tula Falls. If we had stopped in the Piedmont and looked, we would see these other rocks, the Chaga River, which are sediments, and this other one, which is the OPM, and that's called the Poor Mountain Formation. And it's, you know, these are interpreted as morbs, mid-oceanic ridge basalts. There was during these plate collisions, there's just lots of interaction with that mid-oceanic ridge and other basalts that shoot through here. So they occur with lots of, the basalt is the protolith. At this point, they've been metamorphosed, and we call them amphibolites. So all of these are actually amphibolites. So what I did is I went to the USGS site. There are many of these you could look at. This one it has, you know, some good parts and some bad parts. So I struggled, but this one is pretty good. So it tells you that 750 million years ago, Rodinia started to rift apart, but it was a failed rift. It opened up this basin, and thousands of feet of sediments accumulated in this basin. And so if you go to the Smoky Mountains, the Great Smoky Mountains, and all along what we call, the farthest extent that all these sediments or all these rocks were pushed, they call that the foreland. So eventually, if we got on 64 back there, instead of coming this way toward the east, we kept going on the west, we would arrive at the Ocoee Gorge. And the Ocoee Gorge sediments that's where a lot of those are named for. It's called the Ocoee Basin. And you would fairly soon after that, within 10 miles, leave all the metamorphosed sediments, all the metamorphosed rock. And you would pass into what's called the Valian Ridge. And those are the rocks that are underneath all this stuff. And in the Valian Ridge, they're highly deformed. They're folded like crazy, faulted, but they're not metamorphosed. So those are rocks of ages that you're familiar with: Cambrian, Mississippian, Silurian, Devonian. But all this stuff was shoved from far away and pushed over all of that. That's a loud one. That was the garbage truck. So the Ocoee Basin formed, but it was a failed rift. But then, about 500 million years ago, it reinitiated, and we got separation. So that's when all the continents started spinning off. The Iapetus Ocean formed. And then, let's see what date they give. About 470 million years ago, the ancestral North American African continental plates began to move toward one another. And that was what we call the Tectonic, which is, if you're from New England, a lot of things, that's where that term comes from, the Tectonic Mountains up there somewhere. And then after that, we had another one called the Acadian. And most of the peak metamorphism that occurred in the Southern Appalachians is attributed to the Acadian, about 300 to 325. And then after that, there was the Alleghanian. And that's when, eventually, at the end of the Alleghanian, the Iapetus Ocean fully closed, and we had continental collisions going on. So those tended to produce much more upright, large folding events. And something smells dead here. Anyway, that's when it closed, finally, around 250 million years ago, 275, at the end of the Alleghanian. And then shortly thereafter that, it opened back up, and we formed that ocean again. So, this is a complete from a supercontinent to a breakup, then reformation coming all the way back together. It's called a Wilson cycle, probably named after some guy named Wilson. And so, we can just go back in geologic time and repeat that over and over. That's been, the history of what's going on here. And some people are trying to come up with estimates of when the Atlantic will stop opening and will start closing. And the numbers are out there, but, within 50 million, they think it's going to reverse. So just remember, this whole time that the Atlantic's been, opening up, the Pacific's getting smaller, right? That's why we have active subduction on the Pacific. Eventually that will reverse. The Pacific will become a quiescent margins, and the Atlantic will become the new ring of fire. So let's see if there's anything here that we can... So a lot of this information, the tectonic history, I'm hoping that Dr. Fiddler will cover this in more detail, but that's up to her. The units we're going to look at are the Whiteside gneiss, which is also called the Whiteside trondhjemite. And the age is listed here, 466. So that tells you that that's pretty close to the beginning of the Tectonic, right? Given those ages, that the Whiteside is attributed to the Tectonic. Here it is, situated in the middle of everything, and we are going to see, I'm going to show you Whiteside gneiss that's almost barely shows any foliation, which is the alignment of mica, and we'll describe it as schistosity. And that's how we measure foliation, is you look for the alignment of those micas, and when they're all parallel, you're like, okay, now I can measure a foliation. There are rocks I'll show you within the Whiteside gneiss that, or trondhjemite, whatever you want to call it. I call it a gneiss because it's been metamorphosed where they're all just random. You're like, I can't measure anything here. So when you have a large block of a pluton, that there's something called strain partitioning, that when you apply stress, strain is the change in of a shape, length, volume, things are changing, whatever their physical shape is. And so that's the definition of strain. The strain is going to go into the weaker rocks. And the weaker rocks here are the Tallulah Falls, because they're derived from sediments. The two main lithologies we'll look at are a muscovite schist and a biotite gneiss, but on the way up we're going to look at a transition zone where we'll actually see things that look much more like a gneiss in the Tallulah Falls, or ash metamorphic sweep. But this big pluton block, fairly homogeneous, the whiteside gneiss we're talking about, resisted that strain. And so it was taken up by the rocks around it, the ash metamorphic. All right, so that's our overview. This is an old quarry. They probably, when they built the road back in the 20s, they quarried this to build the roads. Since then, they've gone through and redone this road, and we'll see evidence down here. But these have been exposed for, let's say, 80 years, maybe, and it's very hard to see any structure in them at all. So, luckily, in the past 5 years, they decided to redo this road. So right around the corner, we're going to see fresh Toxaway gneiss. Let's go take a look. Even right here, it's only been like 2 years, 3 years since this has been uncovered, and you can already see that here's the water has been dripping on it, and we're already starting to lose it. So this rock here is a great example, and I'll show you more, but what you'll see, and this is common, is that there's a fairly coarse crystalline component here. It's, you know, we're looking at quartz feldspar, and all that mafic stuff is biotite. So it's a classic biotite gneiss, but then you've got a much finer. So how do you have this and that together? My interpretation is that these are two different events. They're both part of the Toxaway gneiss, billion-year-old rock, but these are called orthogneises, which means that they're derived from igneous. You know, their protolith, or their parent rock, was an igneous intrusion. The protolith for the Tule of the Fall, the ash metamorphic, is sedimentary. So there could be, you know, numerous variability. What I forgot to tell you, I was going to, but I always sometimes get ahead of myself, is that the reason this is envisioned the way you see it, because on the way here, we could have stopped down near Whitewater Falls and take you to a place where the ash metamorphic suite / Tule of the Falls is folded into the Toxaway gneiss, which meant that they had to be pretty darn close to each other at some point. So let's walk around the corner here. But if you want to, you know, so all the rocks that, probably some of these rocks are from here, I assume. Others down the, but all of this is Toxaway gneiss. If you can recognize that right there, that's these kind of looks here. Because we'll actually see on our hike today, on the way out, I'll be like, look, that's Toxaway gneiss. It's gravel. It got brought in. Because once we leave here, we won't see the Toxaway anymore. We're on the edge of it. But come down here, there's something interesting to see. Come on down a little more. So behind us here, behind Matt there, this is a pegmatite. They're common to all these rocks. These pegmatites, they can be quite difficult to age, particularly with uranium lead dating, because the, you know, in a pegmatite it's igneous and it intruded, and so you can lose lead to the surrounding rocks. So when you then look at your uranium lead ratio, it appears to be much younger than it is. because uranium, converts to lead. So you're doing that dating, you're looking at that ratio. And when you lose lead, then it looks like it was, came from yesterday, right? But here's the finer grained, and then there's the coarser stuff that occurs. You'll also notice that there's some fracture spacing here, pretty regular. What is it, about 6 feet, 7 feet, repeated over and over. And then there's no, these aren't faults, there's no movement, but these fracture surfaces are places for minerals moving through to reprecipitate, and this greenish looking stuff here is epidote. Extremely common in metamorphic rocks. It's that's a calcium silicate rock. This one has a little bit of it. Looks like some iron stuff as well. Any questions? If not, then we'll proceed to the next stop.
So what did you say was the explanation for the coarser and then the finer on top of that?
I think they represent two different plutonic episodes. I mean, you can kind of see something funky going on here. Look at that, how it just truncates. I don't have a good explanation other than that there's two possibilities: that something else was incorporated into the toxaway gneiss that is of the same age, apparently. I've never actually dated any of these rocks directly, I mean, the numbers I'm getting are from other people. But, I mean, there's pretty clear, you see this inner bedding like that. And that's typically what happens when two bodies, one is intruding into the other. It tends to do it in fingers like this, as opposed to just like come in and occupy it. And we're going to see that fingering today, because we're going to go look at another intrusion of the white side into the Tallulah Falls, and it's doing the same thing. All right, let's tell me when we're on.
Good.
In your guidebook, we're at stop number 1, and it's described as Tallulah Falls Formation and Whiteside Gneiss contact. So I'll have to justify that belief. So let's move up the road and we'll see some better contacts. So you might recall I was telling you that they have inferred several orogenies. And most of those orogenies are based on the idea that you develop one fold set and then something comes along and modifies those folds and new folds show up. And a lot of that is based on, so I'm going to show you the evidence for it, that, we have all these orogenies, but they're saying they came from different folding events. And so as we walk up, the case going to be made is that we're going to try to look at different events and order them. And we should be able to see at least 2 and possibly 3 events. Now these orogenies were also, they weren't, you can't think of them as just like, here it comes, there's a big crunch. They came in pulses. And so sometimes you'd have, folding events from, 2 folding events from the same orogeny. All right, so let's look at this. It's a little more, probably see it just a little better right here. Come up here. If we had stopped about half mile down the road, I could have shown you some classic Tallulah Falls schist and amphibolite mixed together, which is what we're going to see on the hike. So I was like, well, but if you'd seen it there, you'd be like, okay, I've seen it outside and now I can take it in. I can, correlate those. What we're seeing here primarily, this stuff right here, it's pretty darn schisty, but it's sort of more of a biotite gneiss. And it's a transition because, unlike what you learn sort of in basic geology, you can see there's lots of biotite. It's really coarse. That sedimentary environment that the ash metamorphic suite was deposited in the Iapetus Ocean, a lot of it is interpreted as what are called turbidites, or turbidites, sorry. And these are happening on the west coast, off the coast of California right now, where sediments at a, fairly active subduction zone, sediments being shed from the mountains, they're accumulating on the continental slope, and they'll build up, and just beyond the continental slope it's the continental shelf, and just beyond is the continental slope, where it drops off thousands of feet to the abyssal plain, the bottom of the ocean floor. And so as that stuff builds up, eventually it just reaches a point and it just have an underwater avalanche. Landslide, sorry. And what happens when you take up all this mixed sand, silt, and particles and dump them into water and let them settle? You get a finding upward sequence because the sand travels faster. Then the silt comes in, and eventually you get the clay. Okay? Now just repeat this for 200 million years. And you get all these sequences built up, and so these rocks were then metamorphosed, and so you can go from almost a pure sandstone, and in some cases you will see a quartzite in the Tallulah Falls / ash metamorphic. I'll just call it AMS. And then it goes into, and it's totally gradational. It's not like, okay, here's the schist, here's the gneiss, none of that. They just grade from one into the other. So we call it the schisty gneiss. One of my former students called it the scheist. But super coarse. Jack Garahan, who I learned a lot of my metamorphic geology from, he called it the dog's breakfast because it just has everything in it. Okay, so we've established that this darker looking stuff, very biotite rich, is the Tallulah Falls. And within the Tallulah Falls, we see this type of, there's one right there. So we have a quartz. This is called a boudin, which is the French word for sausage, right? I had a German student, and I was like, boudin, right? German word for sausage? And she just looked at me like, it turns out it's French. So we're going to see some spectacular boudins. So these boudins, and they're all, you can see them like little chunks here. That's what all these little weird things are. These were veins that intruded. You can see it like here. And then during deformation, they got folded and they got boudined. And the boudin represents later deformation coming through and actually kind of folding them and cutting them. So the question we have here, what's that? This veins that are cutting through, undeformed, cutting through everything. And what I'm telling you is that this is the Whiteside gneiss. It's a modified, altered, because it's been in contact over fairly large distance. The Pluton we're going to is over there somewhere, right? A mile or so away, where we get into the pure Pluton. But this is that interfingering I'm talking about. That any time we can see something like that, which might even be a pegmatite, but it's coming from here. And these aren't pegmatites, they're not coarse enough. These little contact surfaces, this is retrograde metamorphism, where in contact with maybe even internally the feldspars in there at a lower pressure and temperature, retrograde metamorphism into muscovite on those surfaces. But let's take this a pop. So it's not going to look exactly like what we see. Fact is, this one's pretty much entirely quartz. That just looks like a quartz vein, to be honest. But a lot of them get real quartzy and don't kind of have, you know, barely even see any biotite at all. Fact is, in some of them, you don't really see any biotite. You just see a little hint of muscovite. But this is my interpretation because it was the last thing that happened here. It was recent. And it's not typical of what you see in the Tooele Falls. And so if you're going to be like a halfway metamorphic geologist, you got to look at a lot of rock. And being, you know, having to know your way around the upstate of South Carolina and North Carolina, you have to be able to recognize all these different gneisses and the schist and all this other stuff. And they all have slightly different, and if we'd, like I said, gone through methodically all those thrust sheets and packages on the way up, you would have been like, okay, I think I'm starting to see the difference. But we're just kind of thrusting this upon you. So, you know, I'm not expecting you to become very adept at differentiating, particularly in this transition zone where it's interfingered. So as we move up, we'll see some more interesting stuff that will support those ideas. So here's where we can give some age, okay, based on the folding. And I was here in the winter time and there was like, it was all sucked into about that much water. Obviously this has been highly folded, right? All back on itself. You can even see where, you know, it's almost shearing along the hinge here. So we could say that if we wanted to get, you know, technical, we could say this is F1. That's how they do this, structural geologist. Okay? Then, what about this Boudin here? So the Boudin isn't folded, but it's been, so it was a continuous vein of felsic material, quartz and feldspar, that has been squeezed and Boudined. So F1, this is slightly folded. We could say this is F2. We're looking at two different deformational events. This is how they do this stuff. It takes a vivid imagination, you know. Okay, then again we have the intrusion of the Whiteside gneiss. Here it is, undeformed, unboudined. That's the last sort of thing that happened. So we can infer at least some relative ages based on those sort of observations. Here. So at a trip that we did back in December, we had this, he was like a 10-year-old boy, and I kind of went through all that with him, and then I walked up here and I said, so what happened, you know, what's the age here? And he nailed it. It's pretty good. I'll show you this.
That seems like he's about to ask a question.
See, here's a folded piece. That's at F1 folded. Here's the Boudin, different age, and this is enveloped in its own Boudin. There's like a large Boudin with a fold in it. On the edge is the younger Boudin. So hopefully you recognize this as a pegmatite course. Some of the feldspars tend to form like these, you know, blocky-looking rectangular structures, cleavage faces on them. So obviously this is cutting through everything. So we have something that's even younger than even the Whiteside gneiss fingers. So we've got several ages, you know, that you can sort of put in perspective. And again, you know, if we could go, we tried to age date one of these using uranium lead, and it just was a joke. It didn't work out. Probably there's other dating techniques that would work better. Maybe strontium, rubidium. This is your first spot. Yes. Anybody miss their shower? So you know, when I first started doing this, I came here when the pandemic started. This is what I did. I just started going out and looking at rocks, going on hikes and things. And basically like 2 days a week during the week, I just started doing that. And, but, you know, I was looking at those rocks down there and I was seeing those undeformed layers shooting through them. I still did not recognize them, or I didn't decide that they were whiteside gneiss.
Yeah.
If you're going to get hit by someone, get hit by a FedEx. That'll be a dream come true.
Awesome. A lot of money.
Yeah, yeah. You can retire.
A cat bus is a second dream.
Yeah, cat bus would be a good one. So it was when I came here that I saw this. You know, you can see the Tallulah Falls. Here's the contact. This is Whiteside. It actually goes over there and almost pinches out. That here I could actually see the inner fingering that I couldn't quite visualize down there.
Yeah, Tesla comes with cake. They're like, what the after?
Anyway, this is from here on out is more inner fingering. You know, there's no smooth like transition like, oh good, we stopped, you know, seeing the Tallulah Falls and we went into the Whiteside. They're like this again. And you got to think three-dimensional here, or everything's just not going to make a lot of sense. So, we're good. There's no AMS to really confirm that. And so, it was a little fuzzy. So, we are not quite sure. But at the end of the trip, you should be able to make some decisions, semi-intelligent decisions about where we are. So, we start out undecided. But we're going to do a big loop, 4-mile loop, end up right back here. We're going to come up that trail. See the kiosk down there? We're going to come up on the other side, not through the gate. We could walk through the gate. But that's the trail that takes you down to the most popular spot here called Schoolhouse Falls, where everybody goes to. So everybody you see is going to come out of their car and go that way. We're going that way. So we'll proceed. Probably it wasn't transported from too far. You never know, because it's called float. It's not connected to the bedrock. So unless you can definitely, you know, connect this to rock that extends some infinite distance down into the earth, then you're not sure where it came from. Its provenance is unknown. And that's part of this whole trip is like, is this, part of this or not? At a certain point, you also have to use what you have. You should be able to, if we move this blackberry away, and we're in the high mountains here, and the blackberries have thorns, but they're not, bad thorns. It's a different variety than we have down in Clemson, where those blackberries will rip you in half. But you can see the large feldspar crystals. This is a pegmatite, which, as we have kind of seen before, doesn't tell you anything. They occur in all these rocks.
Yeah.
So if you're going to be a mapper of metamorphic geology, you got to look at the dirt. You got to look at the saprolite. And it can be tricky to differentiate unless you spend some time. In that upper foot of the topsoil, that's the highest weathering potential. So whatever mafics are in that soil, they can get broken down and move around. The iron and magnesium can get mobile, and they can interact with the humic, so you got to look deeper. We're on an old railroad bed here. So back in 1900, this guy bought it to log it. They built narrow gauge railroads. We're going to follow that. So this trail is mostly level, so it's pretty easy hiking. But looking at this soil here, you're like, okay, how do I, what am I looking at? So later on, we're going to look at more soil. So you can't just use the rocks all the time. You have to use everything available at you. Right underneath your feet there. So here's the
saprolite.
This is the whiteside gneiss. It's a what they described leucocratic. It's a fancy way of saying light colored. It's a biotite gneiss, and if you put a hand lens on this one, you will see that there's, some developed schistosity in that plane there, but there's some others that are kind of going like this as well. So it's weakly foliated. And you can look at it and pass it along. She wants to take a look. See if you agree that not all the micas line up in the same plane.
Yeah, they're kind of sporadic.
Yeah, they're subparallel to even, other directions.
Now it's good.
There, it comes out on the front. So here in the trail, we have some rocks that are, so again, you're me, you're trying to figure out what's going on. This is recognized as pegmatite, or quartz veins that intrude along, fractures. So you can kind of dismiss that. But here we have clearly a mica schist. This is a muscovite schist. This is like, when you see this, you're like, yes, ash metamorphic sweet. And the other one here is this, which if you're going to be a metamorphic geologist in the upstate of South Carolina, North Carolina, you better say, there's amphibolite. What we're looking at are those little glittery things. Those are the cleavage surfaces of hornblende. And that's the protolith, parent rock for that was, anybody remember? Basalt, dikes. See how that one's kind of tabular? Other places, you can go and see those oggins. The shrink and swell structures are what they call them. They're not oggins, I'm sorry. They're called, the French word for sausage is boudins. Boudinage. And those could be intrusions, along like sills that were then pinched and swelled. Anyway, you will never see any amphibolite or any highly schist like this in the whiteside gneiss. Whiteside gneiss is pretty much a boring rock, okay? Doesn't have a whole lot of variation. It has some, and you'll see some variation. What it can also get, I think you'll see this really tomorrow at Granite City, is it can become very micaceous. And what I've begun to realize is that micaceous part is when it's getting close to a boundary with the ash metamorphic. If you go into the heart of it, it's just a very boring biotite gneiss. So we've got mixed messages, right? We're seeing whiteside gneiss. If you keep looking down, you'll see, like, here's a chunk right here. And there's we go beat that with our hammer, which we might as well. And see there we have our biotite gneiss. And this one is a little more foliated than what we saw before. The other one was more random. You can see an alignment here just with your, eyes. So anyway, we don't know where we are. But what I'm telling you is that there's a transition zone between these two where they interfinger with each other. And so I'm encouraging you to define these transition zones. If you think it's sharp, then mark it. But I will present evidence to the contrary as much as I can today that we want to be able to. So there's one other rock down here. So don't go too far. Maybe it's here. See, there's more amphibolite. If you haven't seen the amphibolite, get it. Make sure you get it in the sun, because the best way to identify it is to see those sparkling cleavage faces. Here, let's do it for the camera there. If we get a little, you might even catch that. Anyway, out of focus.
I already got the other one. I got the other
Good. Amphibolite.
Ready? Yep.
All right, so you'll notice overhead we have a power line. Boo, yes. So in 1900, this guy from Philadelphia, the story's in there at the beginning, bought this to log it, which he did. And so everything we're looking at is second growth. There's no virgin forest. They're all long gone. They went out on the railroad. And when they took all the lumber, they tore up the tracks and took them with them, because that was pretty valuable stuff. Then around 1960, if you ever heard the commercials, Liberty Mutual. You ever heard that?
Liberty, liberty.
Liberty, liberty, yeah. They bought it. And we were in there's a valley we can't see, but that's the headwaters of the Tuckasegee River. They were going to dam it, build waterfront houses, resort, mainly for their employees. And then eventually, apparently they ran into financial difficulties, or decided that wasn't for them, and they sold it to Duke Power. And Duke Power bought it expressively to blast this power line through, because Duke has all that hydro facilities that we drove through, all those lakes down there, and this is what supplies power to western North Carolina. And building power lines like this, now we're in this situation where, like our President Biden, who I fully support, says that, we need to electrify the nation, but nobody wants power lines like these. High tension strung lines going through pristine places, so that's a challenge. Anyway, once Duke had built this all through, to the opposition of conservationists and everybody else, this place has started to become popular and people knew about it. And the Nature Conservancy bought it, gave it to the Forest Service, and that's why you and I are here. Because it would be like the rest of what we just drove through, where if you stop your car, they come out and politely ask you to leave, or they're calling the police. All right.
What did you say, the Nature Conservancy?
Chunk of rock. So I want you to look at it. And how do we decide whether it's a pegmatite or some part of the whiteside gneiss? Can't hear you.
Grain size?
We could do grain size, but
Banding.
what's that?
Banding.
The banding, the pegmatites shouldn't show, any. We won't call it. We'd rather he brought up a good term, because when you're describing metamorphic rock, there's schistosity and then there's banding, and the banding was very evident in the AMS, but you won't see any banding in here that we can tell. We'll see schistosity. Banding is where there's enough mafic material that you can actually get segregation, a density segregation of the dark and white layers. We barely have enough to do that here. And so this one is, it's kind of sketchy, but there's enough that I would say that this is part of the white side. So you have to make these calls, like, am I looking at, because you can easily be fooled by pegmatite, because when pegmatites invade rocks, they also do this fingering, right? They're intrusives. and they'll often have intimate contact with the rocks that they're intruding, and you'll be like looking at it trying to sift through because there's two different rocks in there and you have to be clever or learn the hard way. So this rock is, I mean, I would guess it was quarried out of the bank over there, but we don't see any outcrop there, and it was moved when they made this thing. I don't think it got moved too far. So you're mapping this, you're like, yes, Whiteside, it's still float. Then we're going to go another 100 yards, and all that's going to be dashed because we're going to go to stop 3, okay? Where you're required to get a coordinate. So right here, classic amphibolite. The way you can often tell these amphibolites is because they have a rind on the outside, because that's where the weathering is. But inside, it's relatively unweathered. So I'm handing off to you. All right? So we have a big chunk there. There's another chunk of, I can't really tell. I think this is schist, though, but it's hard, so it may be an amphibolite. Yeah, it's an amphibolite. Someone kicked it over, and you can see the little red things in there. Those are garnets. So garnets are ubiquitous in the Tallulah Falls Formation because that depositional environment, you know, these turbidite deposits, lots of clays and silts, they contain tremendous amounts of aluminum. So, you know, as you're going down through that whole metamorphism process and you're converting these from sand, silts, and clays to gneisses and schist, and of course the amphibolites are from oceanic, but there's lots of, you know, everything is mobile. So all that aluminum gets picked up even by the by the igneous rock as well. And so you'll see little garnets, big garnets here. Some on the Clemson campus at Forest, there's some garnets that are golf ball sized. You won't ever see any garnets in the Whiteside gneiss, except near that contact. So that was what really confused me at one point, close to where we were, stop number 1, where I was starting to say, okay, there's a transition going on here. I went up the road, it's another 100 yards uphill along the road, and I found what looked like Whiteside, except it had garnets in it. So it had interjected into the Tallulah Falls and interacted with it and sucked out some of that and somehow got garnets in there. Because it didn't look like anything I'd ever seen in the Tallulah Falls / Ash Metamorphic Suite. There's also chunks of, you know, nice chunks of schist here. So my interpretation is that we are going in and out of the transition zone between these two units. We have no outcrop. We have a big chunk of something over here that if you beat on it, you might decide it's Whiteside gneiss. There's a nice chunk of schist here. Still, I don't think any of this is in what we call in place. So, we're good. We'll do it.
This rock?
Nope, we're going to do this one. So, this is the first place that I definitively decided that there's Whiteside gneiss in place. That's a big chunk, and it's exhibiting, you know, a nice little exposure. And we'll see more of these, and I'll have a term for them, what geologists use, where they'll like make up the whole path. We call them sidewalk exposures. And hopefully at this point you've seen enough to look at that and say, yep, that's Whiteside gneiss. You know, fairly fine crystalline. We don't really use the word grain unless it's a sedimentary rock. If it's metamorphic or crystalline rock, we use the word crystalline. So fine crystalline, I can see biotite. I'm assuming the white stuff is quartz and feldspar, Whiteside gneiss. So this could be, I'm not requiring you to, but this could be a mark on your map. You know, we're going to go to the place where we're really going to see an outcrop here shortly. Strike and dip of the foliation, because this is the first place where we actually can see and know for sure, other than that last one where I was like, I'm pretty sure that's this one. There's no doubt that we have, and the reason that we're interested in taking the strike and dip in foliation, you know, just to describe the structural differences. But if we can cross over into the Tallulah Falls and we can see that it has the same dip, strike and dip are very similar, you know, more or less, then we can make that assumption that they were deformed together as opposed to just be totally separate, okay? Because we know they're both old, they're both Taconic type age, and that so they both went through the Acadian, which was a peak metamorphism event. So if they're like, we can actually see them dipping along, then in our mapping, we can extend our map units along strike and be assured, or more assured, that the white-side gneiss hadn't just come up and randomly, you know, cut it off like an intrusion would, right? That if they're deformed together, then they should be continuous along strike, and it helps the mapping process. So, tell me the geology. What did we not see? Good. That's what I want you to do, just because you got to, you know, watch the trail. So, I'm going to let you go ahead, because I'm going to fill up my water bottle here, and tell me when you see something that doesn't, you know, doesn't jive. And eventually we're going to come to a river crossing, and that's going to be stop. You're on the same. Where are we? What page are we on?
We're going to stop 5. We were just to
Stop 4. So we're going to stop 5, and it says pavement exposures at creek crossing. Okay. Yeah, it'll look like this here. There. Well, actually, I don't have a picture in here.
I guess not.
Seems like the picture got lost. That's weird. I don't know. I was editing this, and maybe I, you know, edited it out. But you should see. No? Interesting. Okay. So when you come to where we have to cross the creek, like, and it's all rock, not here. The next one, then we'll stop and chat there. But make your observations between here and there. Go forth and multiply. Because remember, what you're trying to do is refine where that transition zone is. Okay?
No.
How about you? You know what it is?
No.
Can you identify the rock? Coulter?
No.
Can't do it. Anybody identify the rock? Keep walking up here. Come on. Get into it. What else do we see? What do we call that? How do we describe this? The geologic term I already gave you? Or what exposure? Sidewalk exposure. Now, I'm not saying that you don't have sidewalk exposures in the Tallulah Falls. So, but this one is pretty classic right here. This block right here is giving it all away. Moderately foliated. Pretty boring looking rock. What'd you say?
Is it slaty?
There's no slatiness here. It's a biotite gneiss. This is the white-side gneiss. White-side gneiss. Yeah. So you're also going to need a strike and dip here. You're going to need a location and a strike and dip. And the way you're going to get your strike and dip is up the trail. It's going to be very evident, and it's going to you're like, why am I walking on this tilted surface? It's because it's following the foliation. And you'll see it. So that's where you want to measure it. Because we want to get, you know, as many measurements to sort of back up our idea that if we get on strike, we can extend this unit in the direction of that strike and help us to kind of define our map. So, everybody got their lat long location?
Yes.
Okay, good. You can walk. You don't. All right, so we're walking up out of the creek. You can see it back there. Can't because of all the people. But we're walking on this tilted surface, and the reason it's a tilted surface is because it's what we'd call a dip slip, foliation dip slip ledge. So here we see the foliation right there, which they're going to measure. You can turn it off, or you can show it. So you can come and put your compass on this also, you know, so let's ask Andrew. He seems to be doing well.
No.
That, how would you measure, what is the dip angle here? So what does it look like?
Looks like it would be going down that way.
So come stand here and point.
I would say it's going down like that.
Okay, so Andrew says it's going down like this. Now, stand out of the way, Andrew. That, I don't agree with him, because that's just what the apparent. If I look at this overall rock, I see it's going that way. See this angle here? And so when it looks like it's going that way, it's actually going more like there.
That's what I was going to say next.
Next, cool, excellent. So we'll put here's your angle of strike, of dip, sorry, the azimuth of the dip. And remember, we're comparing this to the azimuth of the other dip. And they don't have to be exact, but they have to be like, you know, like close enough. In the same quadrant would be helpful, you know, plus or minus 10 or 20, because we know these, you know, dips are not absolute. These rocks they've been folded heavily, highly. So it's just, you know, can we sort of make this case that they went through the same deformational history, which helps us with the mapping. But Muscovite schist belonging to the ash metamorphic suite.
How do we know this isn't just like float?
Because that's some big float. Float is like there. You would have to explain to me the geologic logic, the reasoning that would, you know, explain why something this large would end up as float. I can't do that. So, but if you can, I'm willing to listen to it. No, it's more like that. Strike is northeast, right? But what's the dip azimuth?
Southeast.
Well, we want numbers.
Should like 150, something like that.
Just based on what we did before. But we want to measure it, okay? We want to get out our compass and physically, you know, take a measurement. And we want a dip angle, because if that also is another confirmation. We have to be careful with the whole dip thing, right? But, you know, if what we saw over there was all 10 degrees, and then we get here and this is 45 or 50, then we're like, whoa, something, even as the same strike, something happened here. But I think you can tell just by looking at it that it's pretty similar strike dip angle to what we saw before.
I got
That way.
I guess. What'd you get?
Is Fred in the shed?
No, not yet. I'm just making sure.
Fred must be in his shed.
And then it's like 52. Okay, cool.
Yeah,
Does that number jive with anybody?
I jive with it.
But what does it mean? If the strike is 50 / what? 230? Northeast, southwest?
Yeah, it's north.
Dip is southeast, right? It's in line with all that other stuff we've been seeing. So what we can do is we can project this to the northeast. That's northeast. And if we find something over there that kind of looks like this or similar, then we could say these are connected. Now, so when you're mapping, one of the classic things to do is, instead of following the strike, which is something you do if you're out west, you can actually follow it. But here, you do cross sections. You cut against the dip. You cut against the strike, sorry. And you try to find lines that then you can connect using that principle. Because probably, if we try to follow this, we'll run into just a big area where there's nothing. You know, we'll be looking at float. But what you did notice also, I had the conversation with Sam. No. No. Dang it. I lost the thread there.
Sam?
Yes. What is it? Matt. That we, from the junction over there, when we hit that amphibolite, we haven't seen anything that looked anything like Whiteside, right? But on the hike in, we were seeing like mainly Whiteside, but with a lot of this. You know, kind of mixed in here and there, like kind of random. We're like, what the heck is going on? We haven't seen any Whiteside, so now we know we're firmly in the ash metamorphic suite. There's no mixture. There's no transition zone. Okay? So that's how, you know, so that transition zone can be, you know, it's going to parallel these if the on strike as well. That if we say, because when we were at the creek, we had the warm fuzzy feeling that we were firmly in the Whiteside gneiss. And there wasn't a transition, right? Because we did that little hike after it. We didn't see any of this stuff. So we were like, okay, we touched into it, but almost everything in between is this transition zone. So don't be afraid, but also you have to recognize when you're in the unit. And you can say, this is, you know, I'm firmly in the Whiteside gneiss. Not ambiguous. Over here, I'm in the ash metamorphic suite. And then there's this thing between them. So how you decide that, you know, you have to use your best judgment. So everybody got a location here? Mm-hmm. Good. Now, tell me when we go back into the Whiteside.
Do we need it? We don't need it.
No, we're good.
the
You can write it down because we did the strike as 50, 230. And I can tell you right now, it's dipping to the southeast at, anybody got the number? About 140 at about 20 degrees. Just based on the strike that we took.
Southeast at 20 degrees. What would you say this is?
That is a piece of quartz that's been colored by iron staining.
Okay.
You know, that iron staining will permeate that quartz, and it'll almost look like it, you know, it's coming from within, but I think it's coming from without, and it diffused in.
Okay.
So,
We're good.
Garnet.
Crossed out of the transition zone into the Whiteside. So, you're supposed to be keeping track, but from here on out, if you see anything that resembles Tallulah Falls, Ash Metamorphic Suite, let me know. Till lunch. After lunch, everything is, you know, back on the table.
You have crossed, between this stop and stop 8, you have crossed back over the
Blank contact.
Whiteside gneiss contact.
So we can stop.
No, I checked it.
So now we're ascending Little Green Mountain, and it's about 100 yards long, and you go up about 300 or 400 feet. That's good. Red light. Do you have the red light on?
Yeah.
Okay.
Snapchat story.
The what?
North end.
No, there's one before it.
The last one was the stop at the turn.
No, this one is stop 10.
Should be 11. We skipped
Last
one.
one
We
was
skipped
stop
10, which was the...
Okay. Well, she says stop 10. Okay, so we don't have one. We're going to skip stop 10. This is just the south end of Little Green Mountain. It is Whiteside gneiss. It's like half of an exfoliated dome because the backside is all vegetated. We're looking out here at the backside of Big Green Mountain, which is very similar to this in that only the western side has outcrops and shows the exfoliation. So there's something interesting going on geologically that I don't quite yet understand. You'll see numerous pegmatites cutting through here and other veins, and so we can see we can look at the relationship between those and come up with some relative ages. As we walk on, so let's continue to walk on. I'm talking as I go. So we have all these plants that we haven't seen before. This is called sand myrtle. It was blooming 2 weeks ago. You'll also notice that in the rhododendron are starting to bloom.
There's some people that haven't caught up.
Yeah, I'm sure. But come on, walk over here. So we have some really interesting plants. This is wintergreen. You know, like if you break the leaves, you'll smell that kind of tea berry. We've got these water grooves, and they're not so much as water grooves as what I'd call water carved potholes. So rocks like the whiteside gneiss that are very uniform in composition. The only way that they can, in the absence of fractures, the only way that water can carve a path is by grinding these little pothole features. Some people argue with that term. They want to call them dissolution cavities. I don't know. That seems more applicable to limestone, but being a fairly competent gneiss, I don't agree with that. There's lots of interesting mosses here. Try not to walk on the mosses because it kind of kills them. But there's a variety of these. This is actually a special case. It's not really a moss. And not being a botanist, I can't really tell you, but we'll see other mosses and other plants.
Slide over there.
So the clearing you see at the end of the valley, that's the, they call that the salt something entrance. That's the other entrance. The rocks on the other side, you can see they look like whiteside. They're eroding like whiteside. They have water grooves. The Tallulah Falls typically doesn't form water grooves because it's the foliation is so strong that it tends to form fractures that don't get widened significantly by the water. But again, you see, anytime you can see nice long kind of dark and white streamers, those water grooves, you're looking at probably up here in this setting one of these plutons, and in this case it's the whiteside gneiss. So what we're doing, we're on the south end of this north-south ridge, and we're going to proceed through this, what is essentially like this garden, I like to think of it. So if you want to, is everybody here?
Yes, sir.
Good, then let's just proceed. This is the best part. So here's a good example here where we've got these, they're very faint. Right here where my hand is, or foot, barely see them. These are quartz-filled veins. So these were formed before the pegmatite, cutting across them right here. So we just see that, there's these pegmatites often in the Tallulah Falls will run, there's probably several ages of them. It appears in a good amount, or most of what I've seen in the whiteside, that the pegmatites were post-deformation. They came in later and cut across everything. There's that breeze. It's gonna feel good today. I was telling Matt, I've been up here all winter and it's not so welcome in January.
Yeah, I
It freezes you off here.
I have more time to hike in the winter.
Yeah, well, it's nicer. So here's a quartz-filled vein running, you know, I don't know if it's cutting anything. I don't see any offsets, but there is an offset?
Yeah.
Okay, so there could be movement there, yes. So in this case here, if we're looking at it and we're saying this one's offset, so we straddle it like this, and we have to straddle it like this, right? So it went like this. So this is called a right lateral strike slip fault, because it's the hand that goes back is the right part. And it'll do it on both sides, right? Right lateral. These bushes here that all look nice and lush, those are all blueberries. And so usually the last week of July, first week of August is when you come picking. There don't seem to be too many on them. Here they are. You can see lots there. That one's loaded. Yeah, let Matt see this. So this just shows you that these quartz-filled veins, we'll see more of this little zigzag fold there. That definitely there was deformation taking place probably during and shortly thereafter the intrusion. You can probably cut it for a while. That was the best part. What are our clues? Causality, right? Does it change?
It becomes more, well, not necessarily, but it looks more quartzy than like that.
Is that a technical type of?
Not really.
How about these over here? This one probably is the best for showing it, because it's kind of evident. What do we see? Horizontal quartz-filled vein. That in this case, the little eyes, as I'm calling them, are forming below it, but in some of these cases they form above it. So we definitely have a more resistant layer. And then what happens? I mean, because we really don't see like water that, we don't see water grooves running in here, right? I mean, there's a puddle up there, but so it may be that, I'm sure water plays a part, but I'm not sure myself. But I think there's a freeze-thaw component that centers around weaker rocks right next to maybe stronger rocks, pure quartz. That differential somehow causes these to form. I see them in other places, not just here, but they typically only form in what we think of as these plutons. These more homogeneous type rocks that, so the weather has to exploit little odd features instead of straightforward like we see in the Tallulah Falls maybe. All All right, one last question, and this is stop 11, so you have to have a point. And what is the strike and dip of the foliation here? And this one's going to be a toughie. A toughie. So what are we going to look for to help us decide? What term did we talk about today that would define the foliation?
Banding?
Well, we said that's not going to show up. Schistosity. We're going to look for that alignment of micas. And what did I tell you about the alignment of micas in this rock? It can be pretty variable. So, but one thing that we're seeing is that nowhere do we see the foliation kind of being expressed like really visibly. So if we use this right here, and I'm using, I got muscovite and biotite here because it is a 2 mica, nice. That I'm seeing them in this plane right there, which is pretty much what? How would we describe that if we were describing strike and dip and it was flat? Horizontal. Right. And so before, remember, it was dipping off to the southeast pretty strongly, right? Here we are on top and it's flat. Does that give us any insight into why this valley is here?
Farm ridge.
So structurally, we're coming up and the foliation flattens out. And I can tell you on top of over there, it's pretty flat too. So we're looking at what we call an aniform. In the absence, if we're not in true sedimentary terrain, then in crystalline rocks, we just use the term synform and aniform because we really don't know what's up or down here. You know, we can't say it's an anticline. I can see that they were originally horizontal and now they've been buckled up like this to an anticline. So the supposition here is that this is a gentle aniform, and whenever you kind of, in geology, you stick something up, that tends to focus the erosion and weathering in that spot. And so, again, the hypothesis is that the top of that aniform was breached and the valley formed. Because between here and there, I can find no evidence of Tallulah Falls. On the very top of that mountain is Tallulah Falls, where it's all forested, but the rocks are whiteside. In between here, it all looks like whiteside to me. So here I'm saying we're firmly in the whiteside gneiss. We were in transition zones. Then we went into what we saw, we interpreted as fully Tallulah. Another transition zone went into the whiteside. So that's how you structurally piece these different readings that you're taking together and try to make, and help your interpretation to back it up. All right, we're good. All of them. Show them what they're missing. Try not to step on the reindeer moss. So we have a folded quartz-filled vein that appears is not as straightforward as one might assume because this limb is folded over. You can also see another quartz-filled vein that's running beside Matt going down. And so these are intersecting. And those, what do you notice about those quartz-filled veins versus this quartz-filled vein?
Not folded.
Not folded. So we have different, this quartz-filled vein could have occurred what they call syn deformation, synonymous with deformation, and that one over there would be post-deformation, much like these pegmatites that we've been seeing. All right, we'll proceed. So we're at Schoolhouse Falls in the Whiteside Gneiss. It's something of a curiosity because from most of the reach, this river cutting through the Whiteside is pretty flat. you know, in a homogeneous plutonic formation, there's, you know, it's not just going to uniformly cut down like a normal. It's going to flow across until it encounters presumably a fracture, I would guess here. You can look and find amphibolites, schist, so we know that the Tallulah Falls is crossing the river up above us somewhere. But we are also, as we'll see, moving on, we're at the edge of the Pluton where it, you know, starts to finger with the Tallulah Falls. So maybe that could, you know, we're in that transition zone. Even though we haven't seen any evidence of Tallulah Falls yet, if we go under and look at all those rocks, we don't see any evidence either. But this is the pattern. Going downstream, runs for a quarter mile, big drop. Runs for another quarter mile, big drop. Eventually it runs out into, it leaves the Pluton and goes into the Tallulah Falls. And then the river just assumes this sort of normal, cutting down gradually, you know, not big drops, changes its nature in the ash metamorphic sweep. Imagine that it can be extended, you know, over to the southwest, which is a long strike, right? Northeast, southwest, dipping to the southeast. So we have it's almost identical garnetiferous schist that we saw earlier.
What stuff is this?
We're going to call it 15.
What if we don't have all of them?
So make sure you have a coordinate.
Damn bugs.
Yeah, there's a net that are. All right. Anywhere. Try it. Yeah, use the. So this is, what stop are we going to call this? 17. Bridge over creek, pavement exposure. But what we've been taught thus far is when you see pavement exposures, we associate them with the whiteside gneiss, right? But at creeks, you know, they can flood and clear off rock, and so we're seeing Tallulah Falls here. So verify that. I mean, you know, one thing I just, you know, never just look at a rock and assume because it looks like it's been what before, it's the same one. You know, if you look closely at the whiteside gneiss on the field trip tomorrow at Granite City, it is extremely muscovite rich. But I think it's because you're in one of those transition zones. But here we have the non-garnetiferous muscovite schist. Remember remember that transition? On the southern side, there was amphibolite. And then we moved into a non-garnet schist, and then we went into the garnet schist. So we saw that we just coming back the other way. We hit the garnetiferous schist, the non-garnet schist, and now we should see what? Before we leave the Tallulah Falls, I guess we'll have to go look. All right. So we're at 18. Where did we hit it? At 8? Was that, or was it 6 and 7?
It should be. Let's see. Let me guess.
I don't know the numbers of anything.
Yeah, 6 and 7. Or 6.
That was where we first saw the amphibolite?
Yeah.
So, if you take your map, if you take your thing here and draw a line on strike, that's where we saw the amphibolite outcropping on that ridge over there. So, we could infer some map units, right? Good. We'll go over and have a beer and watch y'all do it. So, do you know how to put a strike and dip on a map?
Hey Cole, can you point out where
Correctly?
these locations are?
So 18 and 6, you should be able
Alright,
to draw a
'cause,
line between the amphibole
You can show
amphibole
me
rock
here in a few
outcrops.
minutes. So, it's just another 2 months.